Hi everybody. So we're up to our third step, which is all of the substituents. The handy thing about the substituents, it is absolutely everything that you have not yet described. So we'll go through that process real quickly with our good friend citronellal. So citronellal, as I'm sure you recall, that'd be 1, 2, 3, 4, 5, 6, 7, 8. So it's an oct 7-enal. Now, with that, we've talked about our functional group, which is the aldehyde, and we've talked about our parent hydrocarbon, which is an oct-7-ene. What I like to do at this point is circle everything that already has a name. Like so. Everything out of the circle, you got to figure out a name for. Now, in this case, it's very easy. The things that outside of the circle are two methyl groups. So this is a dimethyl octenal. Like we talked about in the last video, we start numbering at the end of the chain that is closest to our functional group. So that would be 1, 2, 3, 4, 5, 6, 7, 8. And that would give us, let me see, there's one at 3, there's one at 7, 3,7-dimethyl. And our whole name is just stitching these two guys together to make 3,7-dimethyl oct-7-enal, or in short, citronellal, but that's a common name and not acceptable to IUPAC. Now, when our alkyl groups are substituents, we take them from their name as an alkane or alkene or al whatever, and we change that ending to -yle, Y-L. So a methane substituent becomes methyl. Butane becomes butyl. So forth and so on. One of those is a little tricky, but we will get to it later. Now, let's go on to our next example that had some substituents on it, and that would be our friend menthol. This will let us work on a couple of things. Menthol, in case you have forgotten, is the peppermint flavor, just like in dental floss. Yes, it was a total coincidence that I actually had dental floss sitting next to me right now. We have our functional group. Step 1 is an alcohol. So we end in -al, not al like aldehyde, -al. Second step, parent hydrocarbon, 6 carbons, in a ring, cyclohexyl. A cyclohexane, I should say. There are no double bonds or triple bonds, so it's an and, not an ene or an ein. That means we go to our next step, which is to circle everything that is not, that has been indicated so far. So the cyclohexane ring and the alcohol. That leaves these carbons here and that carbon there. Now comes the tricky bit. It's a ring, so the functional group makes the carbon that it's on number 1. But we can go clockwise or we can go counterclockwise around the ring. The rule for this is you go the direction that gives the lowest overall substituent number. So if I was to take these two possibilities, 1, 2, 3, 4, 5, 6, that would give our substituent numbers on number 3 and 6. Or I could go 1, 2, 3, 4, 5, 6. Sorry. Hard to get out of the mode of that. 2, 5. 2, 5 is obviously lower than 3, 6, so the greens have it. So we know that we have at the, so now we know that 2, 5 is the lowest overall. And that means that we have on carbon number 5 a methyl group. So we're on step 3 now. Carbon number 2 is more interesting. It has 3 carbons, but the point of attachment is not at the end of the 3 carbons, it's in the middle. We have a couple of ways we could name this. We could brutally IUPAC this and call it methyl ethyl cyclohexyl or cyclohexanol. We never do that. We have a couple of special names that help us out with these. There's actually a bunch of these special names. The good news is there's very few of them that we use all the time that are super handy to know. And those are the ones I want you to know. This one here, where you have a CH with 2 CH3s that's attached to your molecule. That's what that means when there's a little squiggly line across our bond. It means this is attached to another something or other. This is isopropyl. You sometimes see it shortened IPR, but it stands for isopropyl. So a 3-carbon propane group, but it's the isomer of the linear one, isopropyl. Some other ones that are handy to know. We use this one a lot. It is a tertiary butyl group. Which also gets often shortened to TBU. Phenyl's a good one to know. The 6-membered ring with 3 double bonds in it that we've talked about before and you've seen before is benzene. But when it's a substituent, it's called phenyl. That is very confusing because it sounds a lot like phenol. Phenol is a special name for benzene with an OH on it. I'm sorry that the names are so similar. So phenyl is all carbons and hydrogens and is a substituent to a parent hydrocarbon. Phenol is a thing on its own. You can buy phenol in a jar. I recommend you don't put it on your skin. Now let's go back to our molecule. I'll redraw it because it's rolled off the screen. Plus I kind of like drawing menthol. It has this isopropyl group at the 2 position. It has this methyl group at the 5 position. 2 methyl, 5 isopropyl, cyclohexanol. Now this is kind of fun because we have almost completely named this molecule. The 3 steps have given us the functional group. It's given us the parent hydrocarbon, and it has indicated all of the substituents. What it hasn't done yet, and what's the topic of the next video, is indicated the stereochemistry at the 1 and 5 positions, 1, 2, and 5 positions on this molecule. And we'll play around a little bit with R and S and E and Z in the very next video, and that'll give us the full complete IUPAC name of this particular molecule. All right, so we have our full name for everything but the stereochemistry of menthol. Let's play around with something that looks simpler and is actually a little harder. Plus, it lets us practice our phenyl. This is raspberry ketone. Now, this looks nice and straightforward. It actually looks simpler than menthol does. It is a butanone. You can put the 2 in the butanone, but it's not necessary because if you put the carbonyl in any of the other positions, it's either still butanone or it becomes an aldehyde because it's at the end of a chain. But it does not bother me if you call this butan 2-one. Though it is redundant, it's complicated enough that perhaps it makes it easier, and that's not a bad thing. Our numbering starts from the end of the hydrocarbon closest to the carbonyl, or to the ketone. And we just ran into a problem because after we circle all this, we see that we not only have a phenyl group, or benzene is a substituent, but the phenyl group itself has a substituent. It has the OL. We would not call this a phenol. Phenol is not a substituent name. So this is a phenyl with a hydroxyl. And you say, Paul, hydroxyl, where did you get hydroxyl from? Remember that we can very often have multiple functional groups in a molecule. But only one can be the functional group by IUPAC. That means the rest become substituents. We have special names for those substituents. There are obviously a lot of them, and like I've said in the previous videos, Wikipedia has a fairly exhaustive list of them that's quite handy. This is the subset that I expect you to know at the beginning of second year. So functional groups as substituents. Now remember, we are abstracting the concept functional group, so not the actual IUPAC definition of a functional group where there can be only one, but like we would talk about it in chemistry, we're doing a reaction on the alcohol, we're doing a reaction on the ester. That doesn't mean there's not a higher priority group in the molecule. Now this list is fairly straightforward. Stuff like nitriles, which is CN, again, that squiggly line means that it's the point of attachment of the functional group. That would be called a cyano group. So if it was the functional group, and we ran across it in the second video, it would be cyano. It'd be a nitrile. But if it's a substituent to a molecule that has a higher priority group, we would call it cyano. So 2-cyanobutane, for example. So that would be a prefix, as opposed to the names we learned before, which are the functional group names, which are suffixes. Aldehydes and ketones. What we're really doing here is not naming them as aldehydes and ketones, but we're naming them as a carbonyl, and it's called an oxo. So if you had a carboxylic acid, say hexanoic acid, but there was a carbonyl on carbon number 4, that would be 4-oxo-hexanoic acid. Ethers. So some point of attachment and OR. Those would be alkoxy. That makes ethers a little easier to name. Many simple ethers we just name as being the long chain. We call it butane rather. And if it has an OCH3, that would be methoxybutane. 1 or 2 methoxybutane. Amines. Where you're attached to the parent hydrocarbon at the squiggly line, but you can have H's or alkyl groups off the nitrogen. Those are just amino. We will talk later on about what to do when there's more alkyl groups on the nitrogen than just one. It's not as hard as you would think. And then things like chlorines and bromines and iodines and fluorines, and that one I can never remember the name of because it's radioactive. Cl, that would just be chloro, or bromo, or iodo, or fluoro, or so forth and so on. Now, back to raspberry ketone. Oh, and alcohols, of course, which I said but didn't write. That's hydroxy. All right, so we've got a butanone. On our butanone is a phenyl group. On the phenyl group is a hydroxyl group. That is the order that you think of it. So the hydroxy group is a substituent of our substituent. So we have 4, that's this 4 here, 4-hydroxy phenyl. Sure enough, 4-hydroxy phenyl. So this second 4 is taking our substituent, phenyl, the point of attachment is always carbon number 1 on a substituent. We count around 1, 2, 3, 4 on the substituent. It has to stay in the parentheses to make sure that we're sure that that 4 refers to our substituent numbering and not our parent hydrocarbon numbering. So here, this says it's the 4 position of the phenyl, not the 4 position of the butanone in this case. So that's 4,4-hydroxyphenylbutanone. Now we've indicated the molecule. Again, you could have written butan-2-one and it wouldn't have bothered me. It's not technically IUPAC correct, but it shows plenty of understanding in the material. Okay, that was fun. We did 2 things there. Names of functional groups as substituents and how to have substituents on your substituents. So that was a pretty big leap, really. And when you've had a big hard work day like that, you should really go home and have a little meth. I'm kidding, don't have meth, it's bad for you. This is meth, or N-methylamphetamine. Now, this is a first step into this one, so why don't we go through it tiny bit by tiny bit. If I look at this molecule, the clear functional group, 1, is that it is an amine. My parent hydrocarbon is a propane, 3 carbons long. And you say, but Paul, you always put the nitrogen, or the functional group, numbered so that it has the lowest number. Well, this is 3 carbons. So you can go from the top down, 1, 2, 3, or the opposite of that. Either one would be following that rule, right? So then you slide into like you did with the rings, where you want the lowest overall substituent number. If I go the way I ordered it, the phenyl group ends up on the 1. So it is a prop, and because it's a straight alkane, so that's propan-2-amine. Again, you could write this as 2-propanamine. I find that a little less clear personally. Now, when we go to step 3, first we start by circling everything that we've named to date. We have a phenyl group at the 1 position. That's nice and straightforward, and we've had practice at it. And we have this methyl group on the nitrogen. The nitrogen doesn't have a number, does it? That makes things a little bit more wacky. The good news is the solution to that is easy. You just write N-methyl. Super. So our full name of this is N-methyl, 1-phenyl, propan-2-amine. That just barely fit in the spot. Now you might ask yourself at this point, now that we've done 2 of these that have multiple substituents, how is it that we list them in the front? That is both simple and tricky. We list them alphabetically. So here, M for methyl comes before P for phenyl, so it's N-methyl, 1-phenyl. That's straightforward enough. If you take a quick look back, however, you would say, hey, Paul, did you screw up? Because for menthol, you had 2-methyl, 5-isopropyl. That is tricky. And that is because we don't count things like iso and tert or N, or sorry, not the nitrogen N, but the normal N, which means a chain. We don't count those in the alphabetization. So methyl would technically come before isopropyl, because isopropyl is really a P. I don't actually care that you know rules like that. Back in the day, I think I've mentioned this before, we had to actually look things up by their IUPAC names, and getting the orders right meant that you actually found your compound. and didn't make the embarrassing mistake of saying that you were the first person to make something when you weren't. Nowadays, we have structure searches, we have the internet. We actually really didn't have the internet when I was in an undergrad, at least for chemical stuff like this. And the only web browsers we had were text-based, and we banged rocks against each other to count. It was a hard old time. So don't worry so much about the alphabetization in the front. If you have the need to do it absolutely right, that is the way to do it. Now, the cool thing about the N thing, the N-methyl, is that it works for amides as well. If you were to take something like butanamide, and you have two methyl groups off that nitrogen, this is an amide if a carbonyl has a nitrogen off it on one direction and a carbon or a hydrogen on the other direction. That's called an amide or an amide, depending on your regional accent. This has 1, 2, 3, 4. So step 1, amide. Step 2, but, an. So this would be a butanamide. That would cover off everything inside the circle here, which is everything except the two methyl groups. So that would be NN dimethyl, as in my methyl groups are both on the nitrogen, butanamide. Sadly, esters are more difficult than that. With esters, we have to do a little bit of history. The way esters were originally synthesized in the lab was a condensation reaction of an acid and an alcohol, where R prime is just a different R group, giving you an ester and if you balance out your atoms correctly, you realize that the other product is water. Now, because of that, we name esters, treating them kind of like there being an amalgamation of an acid and an alcohol, where the acid is the functional group side that determines what the parent hydrocarbon is, and the alcohol side is considered sort of a substituent. So if we were to take a real ester, I started with banana oil. That's a good choice. So here's a real ester. This is the essence of banana. So if you buy banana flavoring at a store, it's this guy. If we were to look at this through that oxygen that has two different things on it, this would be our alcohol side. This would be our acid side. So our acid here would be ethanoic acid, which you probably know as acetic acid. The upper name is brutally correct IUPAC. The bottom name is actually a common name, but it is so universally used that IUPAC accepts it. So that's that side. The alcohol side is a 1, 2, 3, 4 but. With a methyl group on the 3 carbon. It actually doesn't matter if you go up or sideways in this case. 3-methylbutanol. The common name for this is isoamyl alcohol, which is sort of in the same general category as T-butyl and isopropyl, because there is a T-butanol and an isopropanol. But for the purposes of this course, anything more complicated than that, like this is, we will realize that it gets called isoamyl alcohol, but the process I want you to reproduce and the thing you need to remember is direct brutal IUPAC, which gives 3-methylbutanol. When we combine these together, this would be 3-methyl-butyl. So now my alcohol, you get rid of the OL, and you call it YL as an alkyl substituent on that oxygen. So this is 3-methylbutyl, where the 3 describes the butyl. Ethanoate. That is the strict IUPAC name for this. Since we tend to call it almost always acetic acid, you can also replace this with 3-methyl-butyl acetate, which is a much more common way of naming it. Both of these are correct. Both of them would be acceptable if I asked you to name this, for example, on an exam. Or if I wrote either of these out, I'd expect you to figure them out because you will see acetate enough that it's going to be considered common by us. I wouldn't actually, however, give you the name isoamyl acetate. It's fun to be able to recognize this, but I would never write this on an exam and say reproduce it. Because I don't think I've ever done that. Because isoamyl is too arcane for me to expect you to know. Let's do another example. This is a flavor molecule that is added to fresh orange juice to make it taste more orangey, or that which they call fresh orange juice. So again, draw that hashy line there. We have our acid, which is butanoic acid. We have our alcohol, which is ethanol. So this would be very simply ethyl butanoate. Or somewhat more old school, ethyl butyrate. The tierate and the anoate are new school, old school. I show the butyrate because I have to. It's actually IUPAC legal. And also because you run across it here and there. But you'll notice already we have the "an" in here indicating that it's an alkane. So it is, I think, a much clearer way of naming esters. And that is it for this video. Obviously, we can go on and on with this and further. But they actually follow all the rules that we've gone through in this video already. There's not much more to it than what I've already given you. So from there on out, it's just a matter of doing examples, which I will do a 5-6 video, just doing a handful of examples together, getting more and more complicated. But from here, you should be able to name everything but stereochemistry on at least reasonably simple organic molecules. Nothing carried away like cocaine, for example. But plenty of pretty much everything you will do in the first term is covered off by what we've done already, except, of course, stereochemistry, which we will get into this term. So the next video is exactly that. The stereochem video will not focus on the physics of stereochemistry, but rather just the naming of stereochemistry. The physics of stereochemistry and the way that it rotates plane polarized light and chirality and its effects on everything because we're chiral beasts. That's actually a whole chapter we'll deal with in 213. So for now, toodles. I'll talk to you in the next video.